let's welcome Professor Capasso.
Thank you very much for the introduction. So this is my opening slide, and you already heard the topic, so I'm going to move swiftly to the next. So metasurfaces are a way to control in an arbitrary way the wavefront of the incident light. So typically we have a surface that is nanostructured with phase shifters. There are typically can be pillars, can be basically they can have different shape. They can even be in the future, there'll be free-form elements. And the idea that you can, these are sub-wavelength space, so you can locally engineer these wavelets, and then using Huygens Fresnel principle, you take the envelope and you find the actual wavefront. And the benefit of using metasurfaces is the following, that you can lithographically define them. And in this case, all the elements have the actual same height. They're simply digital type of structure. There is nothing sort of graded, and that makes the processing simpler. The small footprint, you can even vertically integrate several metasurfaces. I'll show some example. The key point, which is central to all of this area, is that is the unprecedented control of dispersion. By changing the lateral dimension of the metaatoms, essentially what you can do is change the overlap of the incident light with the structure here, so you can locally change the effective refractive index. You can see these as tiny waveguides. So there is a lot of engineering possibility of the dispersion that is not available with conventional diffractive optics such as Fresnel optics. It's also easier to control the aberrations, and importantly, you can also access multiple functions. And this is sort of the vision. I already said that you can provide arbitrary control of the waveform technologically, and we are here now. This is not the future anymore. This is happening as we speak. The same foundries that manufacture the camera sensor can manufacture the metalenses using the same technology, typically deep UV lithography. So the future, and it's very exciting for high volume markets, is CMOS compatible flat optics. So I will dwell on this, and I will also talk a bit in the end about the interesting physics, in particular structural light, that allows you capabilities beyond what you can do with spatial light modulator. Finally, even though I'm not going to spend a lot of time on it, we see increased role of inverse design, co-design of hardware and software, and generally the impact of AI on photonics. So this is our demonstrations a couple of years ago, 3 years ago, that we could make a planar lens. In this case, the metaatoms are still in the, this is made of glass using deep UV lithography. So we could demonstrate diffraction limited performance with a high Strehl ratio of 0.95. This lens is 1 centimeter diameter, and you have about 160 million nanostructure per lens. So this shows the more than an existence proof. After this paper, there was a lot of interest from companies and so forth. And recently we decided to push, can we push this to the limits? So this is preliminary work, not published yet, where we made a 10 centimeter diameter lens. Again, this is made of glass, optimized for the red. This lens contains about 18 billion elements. And you see, this sort of captures the significance of flat optics as opposed to conventional optics. There is a reduction in thickness. There is a significant reduction in weight. You can use standard materials. glass semiconductors in particular, and other type of advantages. Now, with that, I do not want to say we're going to replace refractive optics, period. It all depends on the application, but there are some high volume applications, such as camera module for cell phone, for laptops, for sensor, where really metalenses will have a major impact and will be made the whole sensor basically with the lens, the whole camera module by the foundry based on the design. Right now, there are two separate technologies. The optics, that needs a lot of alignment with multiple lenses, and the sensor, which is standard CMOS process. So we characterize this, again, this is preliminary work, so there are still things that have to be improved. The spot is not quite diffraction limited, but it's reasonable, okay? And the efficiency also could be improved. I mean, in the central part is 65%, but in the side, in the peripheral part, because of some problems with the fabrication, we are not quite there yet. And but we decided, you know, to sort of my students to have some fun with this, to mount it in an actual telescope with a filter and to look at a nebula. And the images we talked to some astronomers are actually pretty good. Okay, this image of the Orion of the North American nebula, and if you compare it with, you know, with what has been obtained by other optics, it's quite a good comparison. So I certainly see that there are also some application of lenses, if we can make them large, as I said, 10 centimeter for science. I want to go straight to the technology. A few years ago, I started with my former graduate student, Rob Devlin, this company called Metalenses. And the idea, based on the fact that the same technology can be used to make the sensor and the lenses, to really target the high volume market. We now went to a round B of investment. These are some of our strategic investors like Intel, 3M, Applied Material, and BCs, and so forth. So this shows an existence proof. What you see at the center is a wafer of glass with 12-inch wafer with 10,000 amorphous silicon metaoptics, which are designed for the wavelengths of vertical cavity surface emitting laser. And the target markets, yes, it's, for example, face recognition in cell phones and actually so forth. So this is quite exciting news. And recently there was an announcement. In fact, sorry about this. Yeah, let me go straight to cut to the chase. Metalenses has partnered with STMicroelectronics. You know, it's a major semiconductor company to deliver the world's first optical metasurface technology. And the target is next year, and for application that you can actually see here. So, and here again is Rob Devlin, co-founder of Metalenses, holding up this 12-inch wafer with the Metalenses. One of the advantages for sensor, I'm going to step back one slide, is here. On the left, you see a conventional sensor. So there is the sensor chip. And on top, there are multiple lenses of different material, refractive lenses, plastic lenses that have to be aligned extremely carefully. And what you can see is that the intensity tapers off as you go to the edge. This is physics. There is no way around it with the refractive optics, unless you decide to make a monstrous complication. Basically, the intensity will fade away. So you can see to the right, to the top, with the four plastic. There you see the intensity fading. Okay, metalenses. With metalenses, you can do the work of 3 or 4 lenses with just one lens and an actual aperture, and you can make the optics so-called telecentric. So as you move out toward the edge of the field, the intensity remains maybe remains much more uniform. Now you will notice some distortion here simply because the distortion is not intentionally being corrected. Normally that's done by software. But other than that, you see, this is a very promising comparison. Now we are talking here of lenses that are not corrected for chromatic aberration. On the other hand, there are tons of application in sensing, in LiDAR, face recognition, where an achromatic lens is actually not needed. Moreover, achromatic diffraction limit is definitely in many cases just an overkill. So we have to keep in mind what's the application we are after, and then decide what technology to use. Now we have been looking at ways still. I'm going now to switch more to the research. In research, we have been using a platform for visible light based on titanium dioxide. And titanium dioxide is a completely transparent material in the visible, almost completely transparent, which has good refractive index around 2.5, so you can strongly confine light to it. And so our goal has been to make achromatic lenses across the visible, but initially also, let's try to make an achromatic lens at the RGB colors, actually. And in fact, I'm going to skip this and show you straight recent results in collaboration with a group of Steve Johnson at MIT. So the goal here is to design metalenses that are 1 centimeter diameter, that are show diffraction limited performance with identical, as much as possible, focal length for the 3 primary colors. So this is a very challenging job. So it was approached by our people by inverse design. What you do in inverse design, you determine an objective function, which is a function of the parameter. You start with a random design initially, and you evaluate your objective function. And then using a method called adjoint optimization and a fast solver, essentially you do a series of iterations where you compute the key point is the gradient of the objective function, until eventually you actually converge to a situation where you basically stop because you've got an arbitrary close to it. This is a very efficient process. You can see the results here. Without inverse design, we wouldn't have simply been able to do this. So you see, you have the maximum focal length shift is 0.03% of the design focal length when you move from one wavelength to the other. This is a very important demonstration of what can be done. In fact, this is more to show the capabilities. That like me, that VR is still not a large market, and VR, AR, and the augmented reality is basically tiny, if not almost non-existent. So there's still major problem to solve, but it's a promising research area. So here we implemented a simple virtual reality platform with a meta-ITs, a laser illuminated micro LCD. You see here the whole setup, and what we have achieved is on this near-eye display, high brightness, wide color gamut, and I'm going to show you some results here. It's an interesting kind of existence proof that it's a promising area to pursue. So you see good binary image with well-resolved pixels here, also good grayscale image and good color mixing result. And also we have here a VR movie of a running cat with this refresh rate. So what we are after again is to make achromatic lenses across the entire visible. we already demonstrated that using forward design, that the limitation was the diameter, maximum around 50 microns. So we are now going after using inverse design and bilayer metasurfaces using free-form optics. We have started to work on this platform here, making metaatoms that have a free-form titanium dioxide metaatoms. We have glass nanofilms and a matrix, and then you combine them. You see, these are actually the SEM picture of these. You can see the top of these, which are free-form meta pillars. So it's there are some really good capabilities. So the goal here is to, first of all, what can we do here? Well, we decided to we increase the diameter to 110 micron. Here, this again is a double layer metasurface, which you can see here. And we have achieved, in fact, from the visible to the near IR, essentially, I call it quasi-achromatic behavior. You can see, actually, this is actually a small shift, okay? The spots are indeed diffraction limited. So again, this is a promising direction, and our goal is to, within a year, to realize an achromatic lens of diameter, you know, that approaches initially several millimeters, probably 1 centimeter. Again, this is a single lens that covers the entire range from the visible to the near IR up to 900 nanometers. And yeah, the focusing efficiency, I want to make a statement about the focusing efficiency, okay? So the commercial metalenses I showed before, made by Metalenses, the efficiency exceed, they are designed for the near IR and a focusing efficiency of 90%, okay? And in our lenses here, the ones that I call nearly achromatic, the focusing efficiency varies from 70 to around 90% in this wavelength range. If we allow for chromaticity, then we get a bit higher efficiency. So we are on in the direction to maximize the efficiency. It will never reach the efficiency of a refractive lens. The question you've got to ask, it depends all on the application that you want to pursue. We have also working on a complementary platform. How about making nano holes? Right, there would be some advantage here. You can increase the aspect ratio more than than what we can do in titanium dioxide, which is 20 to 1, and they are more robust and so forth. So we decided to implement the strategy in actually silicon, and using silicon holes made actually using the Bosch process. Okay, this is what we did. This is a membrane here, that a holy membrane that it's designed to actually focus light. So you can see here the results. They're pretty good, and this is a first step. But I think this technology is actually promising also on a different type of account. You can use the holes as to fill them with certain material. This could be liquids, you know, maybe liquid crystal. So there is some interesting possibility given by the ability to fill these holes. And these are the results that are very, very good, I must say. This was optimized to work at, I think this was in the actual red wavelengths here. It's perfectly diffraction limited here. If you look at the modulation transverse function, it sits on top of what you expect theoretically. And this was inverse design. The effective index profile used for this lens was obtained by inverse design. One thing that I want to stress, you see here, there is a lack of multi-focusing. every diffractive lens has to have multi-focus, and also ours have them. But you can minimize their intensity to be essentially negligible compared to the main focus, something that you cannot do easily, almost I would say impossible to do when you use a Fresnel lens. This is the latest thing, which is unpublished work where we decided to see how short can we push the wavelengths and can we do to the XUV. Of course, there are interesting applications, you know, for XUV, the lithography, but for that you have to make pretty large lenses. So we're really here motivated by the science, okay? And the science is there's a lot of physics which uses XUV, high harmonic generation, essentially to achieve attosecond pulses to observe the motion of the electrons in atoms, molecules, and so forth. But there is looming also the XUV technology. You know, there is a company, ASMS, that makes this. In fact, they are commercially available. So our goal eventually, if we can make these lenses large enough, we also think about how they could be useful for XUV application, for technology, basically. So let me fast forward this. So basically, this is the principle of high harmonic generation. 1 attosecond pulse is generated every half cycle of the driving laser pulse, which is IR, in an Argo field tube here, and you create high harmonics, harmonics of the incident frequency. This work is done in collaboration with a group of Martin Schultz at University of Graz, but they are experts in these measurements. Now, the design is quite challenging and very interesting. We actually picked a wavelength of 50 nanometer, such that in this region here, the material has a lower silicon, has a lower refractive index than actual vacuum. It's less than unity. So the vacuum is actually guiding. So this provides a very interesting, you can make a very thin device with actually no substrate. So now you can ask yourself, is it worth it to go through all this effort? For example, in this area, people use the Fresnel zone plates. Well, this is a simulation comparing a Fresnel zone plate with a meta lens in this frequency region, and you can see that the focusing profile is actually much cleaner as expected. And I'm not going to dwell on the fabrication, only to say this was an heroic effort by my group to make this. So at the end, they were able to make 2 small lenses that, however, you know, could do the actual job, and they were tested with this attosecond fact. Let me show you the setup. Okay, I think I forgot to show the setup. Anyway, essentially, you hit the sample with all the harmonics, but then you interrogate. You're only looking at the 21st harmonic, which is the one for which this meta lens has been designed, basically. And again, you see the sample here, and the way the beam waste was used, you know, this is an area where you don't have optics, essentially. So what are you going to use? Where you're going to use the well-established old methods of using the actual knife edge. So by moving the knife edge in and out of the focus in different positions, you can actually get the beam waste. Again, this is a well-established method. It works well here. It's close to what has been modeled. Okay, and so it's again, this is an existence group, and we are ambitious, so we want to perfect these small lenses, but eventually go to large diameter and see what happens. I want to next move to application in communications. We have been collaborating with a group at Corning for the last 3 years. we look at metasurfaces for data communication. Now, everyone knows that after the telecom bust, things have recuperated, and now the really important area is to go beyond the capabilities of wavelength division multiplexing to use spatial division multiplexing. And this, for example, is for applications such as server farms, where you have to transmit a huge amount of data, not on a significant distance, maybe 1 mile and so forth, but you need to get a ultra high capacity. And there are several strategies. One is to use multi-core fiber, parallel fiber. We have started to play with Corning with few mode fibers. So we wanted to demonstrate proof of principle, experimental through fabrication. So with a metasurface plasma, we could make a max Dmax, particularly a multiplexer, okay, for a few mode fibers. That was the goal. And so, so the idea is very simple here. This is a 3-mode multiplexer. Okay, so you have the input is different single mode fibers, and you want to encode the capacity of these into the 3 modes, LP01, linearly polarized mode of a few mode fiber made by Corning in fact. And then eventually have a demultiplexer. We demonstrated the multiplexer here. This is a very challenging type of design. Why? You have multifunctionality in one metasurface. You have collimation, focusing, beam deflection, mode conversion. So this is a case that it's literally impossible to do other with inverse design. So this was a very nice challenge for us in terms of design and potentially do something useful. The platform we use, we only work with platforms that are technologically established. So in this case, we use the amorphous silicon pillars and so forth. So you see how the metasurface, so essentially you have the single mode fibers here, and then you have at the output, okay, depending, okay, on which input you use here, you will have either, you'll have these actual modes here, and if you have them simultaneously, you will have these output modes, these modes up here where my cursor is. These are the dimension, and this is the process. It took quite a long time to develop it to our satisfaction. And what we did then at the end is, the mode imaging. So these are the target modes. Okay, we use 2 types of design, and these are the optimum design. We get, in fact, good replicas close to the desired for the LP1 and for these 2 modes, a bit less so for this, but again, this is work in progress. And we show that a design wavelength of 155 micron, we could really minimize crosstalk. So again, this is a good existence proof, a promising direction, which we hope to pursue in the next 2 years with Corning laboratory. This is not so close to application, but still very promising. And it's how about doing free space active photonics here, which you have application in beam steering, coherent laser ranging, and so forth. So here we design, again, to use an existing platform. There's been tremendous progress in the last 10 years in organic, in polymers with high electro-optic coefficient. The pioneer is Professor Larry Dalton at University of Wisconsin. And so this is a collaboration with them, okay, with his group. And the idea here is you have an interdigitated structure, okay, and you have nano pillars. In this case, they're of silicon. I'll describe them later. And this is embedded in a matrix of a electro-optic polymer, which has extremely high coefficient. So the idea is to make a modulator. First of all, you have to pole in order to get this high electro-optic effect, you have to pull these organic layers, and you do that by applying a static field between these integrated type of electrons. Then after you are done with this, you can apply the actual modulation, and the modulation essentially via the electro-optic coefficient, because you change the refractive index of the material in which these resonator they are embedded, you can shift the actual resonance. And it works pretty well. I really think this is a very promising for application, because organic materials and electro-optic polymer in particular are past the stage of just basic research. They're essentially waiting for new types of application, and we decided to go after that with actually modulators, okay? So, sorry. So these are the structure. These are, I call this hybrid silicon, the organic photonic. We take a cross-section, let's say. Forget about this curve here. I should have taken it out because it relates to another structure. So these have modes, confined mode, that are called quasi-bound state in the continuum. There are strong resonances that you can and narrow that can have a high Q. So by applying a bias to these electrodes, you can actually shift this resonance via the electro-optic effect. You have to orient the field, the modulating field, in the direction of the dipole of these, as shown here, right? And then you are ready to do the experiment. Alpha is the angle, simply is there is this. Alpha is the actual parameter. Theta is the angle, if you can change the orientation. And you can actually see the kind of transmission that you have. It changes as you change this orientation angle. The key point, you have very sharp resonances, and you can actually tune them. You can tune the transmission. We change the bias from -100 to 100 volts over a significant range of resonances, of wavelengths, with a significant Q factor. In fact, the Q factor is about up to almost 1,000 D, depending on this parameter, which is the orientation of these elliptical nanopillars made by silicon. And these are just the raw data. Okay, we didn't make any attempt, to correct for cable calibration and so forth. But it's a standard setup. Proline setup here, but essentially the key message is we have a response out to a few gigahertz cutoff frequency, and this puts it in a range, interesting range, for example, for free space type of application and so forth. So I think this is a promising direction due to the fact, again, we use the platforms that are now beyond research, such as the electro-optic polymer and so forth, and of course we use silicon nanostructure and so forth. The last part of my talk is about structural light. I think everyone in the audience have heard that you can make that light does not only have spin angular momentum, but if you have a helical phase count, basically the Poynting vector follows a spiral. Okay, the beam has optical angular momentum. Optical angular momentum in this case is defined as the number of twists of the wavefront within a wavelength. So if you have only one twist, complete twist, you have an optical momentum of 1. Now you might say, is this quantum mechanical? Absolutely. There's theory and experiment showing this is valid at the single photon level. If you have a paraxial beam, then you can neatly separate the spin and the orbital angular momentum. Okay, and so this has done a lot of fundamental research, but also application. There is application because optical angular momentum is an infinite basis, right? You have an infinite number of these eigenmodes with different things. We use them, for example, to encode in information and so forth. And it's an active area of research. In fact, we are doing this for the fun of it, to look at the The physics, I want to stress that this is a singularity. If you look the vortex head-on, okay, what you see is that center is intensity zero as the phase is undetermined. It's called the line singularity. Now you can visualize the spiral wavefront by doing a simple interference experiment between your vortex beam and the incident beam on whatever has generated these beam. You can use liquid crystal platelets, you can use metasurfaces, and so if you interfere the incident beam with the helical beam, well, the equiphase point are simply spirals, and so you can say that this is a head-on image of the spiral structure of the actual wavefront, and the number of branches in the spiral tells you actually the optical angular momentum. So it's kind of neat. You can do some nice experiments. So with my students, I've been asking the question, can we make more general type of singularities? Can we make a singular surface, a surface that is dark and it's singular? It means a surface of ideally arbitrary shape, zero intensity with undetermined phase. That's scientifically an interesting question, but there is more to it, and I can anticipate what it is. Okay, you see the light has the diffraction limit. You cannot make a spot really significantly less than the wavelength. Well, you can use special techniques, but basically you are limited by diffraction. Now, but in the dark, you can make a dark region as small as possible. So think if you can make beams of light where you structure the actual dark part of these beams. Then for that, you will be able to interrogate, for example, materials at a scale not easily accessible by other methods. You could probe defects, defect starts only with point defects, failure mode, which are at the atomic scale. So maybe such techniques could be used to study the cascade of turbulence. So we are thinking long-term of some interesting application of this complex singular light. So to describe these generalized singularities, we note that a complex scalar field has a real and imaginary part, of course. We know that, and so if you want to have a singularity, the real part and the imaginary part must be zero. So the phase is undetermined, which is the ratio of these two parts here. And these intersection of surfaces give you the singular region, right? So this is the line singularity of a vortex beam that I told you before. This is a zero-dimensional singularity with the real part and imaginary part equal to zero meet at one point. And this is a surface. So we ask, can we design a surface that is singular? The answer is yes. And there's a lot of massive computation behind it, which now I'm literally sleeping under the rug. But the idea is to find a singularity to maximize the phase gradient orthogonal to the desired sheet. So we specify a particular sheet of dark that we want to create. And so my creative student decided to make a metasurface that literally could generate, when light is incident on it, this is at a wavelength of the green with titanium dioxide nanopillars, a singular surface, okay, heart shape. And then optically, you can scan your, if you like, your camera system in a way to interrogate plane by plane the singularity. So this is a simulated intensity. This is an image of the measured intensity and so forth. So these results, though they are preliminary in a sense, we published the first paper last year, I think are very encouraging of what you can do with the singular region other than line singularities. Okay, this is the setup that was used. Okay, to do the imaging, and you can see here we are looking along the propagation direction. So you hit at some point a situation where you really see the singular region. There is still quite a bit of background, but it's unmistakable that we have that we have a singular region that in shape and quantitatively is very similar to the simulated singularity. But recently, we have had good luck, I would say hard work, not good luck, by my students to inverse the line of a metasurface, which has a cylindrical phase profile that creates an array of zero-dimensional singularity. These are these spots here. The intensity is zero here. In between, there is light, and the phase is undetermined. Okay. Now, you might think, what is the application? Well, scientifically, this could be used as a detuned trap. You know that if you want to, if you have glue the tuned optical trap, if you use the methods of, if you use the red detuned trap, you know actually that you can trap a particle in a high intensity region. I mean, that's the reason why Askin got the Nobel Prize in Physics 2 years ago. If you create a blue detuned trap, then you can use it. You can actually have the particle confined in the actual gas region. So this is a possible application. So the idea is this was a strategy. So this was done by inverse design, create a set of singular points by maximizing the actual phase gradient, okay, and then enforcing trap uniformity, which is really hard, okay. And this is a technology that is really beautiful metasurface. It's made by my group, again, with titanium dioxide. This is a combination of e-beam lithography and atomic layer deposition. And these are the experimental type of results here. You see the experimental intensity here. These are actually it's a vertical cut. This is the actual position here. And this is actually the transverse Y cut. It's the transverse plane. You see these one here, these dark centers here. These are the singularities. I think so. We are on this has certainly a number of interesting applications. And this basically brings me to the conclusion of my talk. The metasurface can provide arbitrary control of the wavefront. Technologically, I think we are at a turning point. Metasurfaces will capture large markets based on the fact that the same foundry can make the CMOS and the metalenses, and in fact, other metasurfaces for the future. I told you a bit about the science we are doing with structure light, structure dark, and I tried to emphasize the importance of inverse design for the future of optics. And none of this work would have been done without a fantastic group of collaborators over a number of years. And this is in particular the last, 2016 to now. I mean, some have now left, some are current students. I also want to acknowledge colleagues like Steve Johnson at MIT, very important for the contribution of his group on inverse design, Professor Jing-Sing Chen at BU, and Todd Ziegler. Actually, I didn't have time really to talk about this work, but he's an expert in computational imaging. And last but not least, the group of Doug Werner at ESU, where we are collaborating to do freeform metaoptics. So with that, I thank you for your attention.
Thank you very much, Federico. Thank you very much for the very interesting talk. Now, we are now in the Q&A session. If you have any questions, please type in the Q&A panel at the bottom of the Zoom screen. So we have two questions already.
Yeah, the first one is for the inverse design of RGB achromatic lens. What about the performance of the wavelengths in between RGB? Well, the short answer, the focal length changes. You start to deviate from the diffraction limit, but it's not a dramatic type of effect, okay? So it's kind of gradual, okay? I don't have the data in front, but we definitely have looked at it. I also want to add that recently, and I didn't have time to show the result, we have made an RGB lens which is achromatic for 6 different wavelengths. And again, the focal lengths were identical, you know, within 0.02 or 0.03% of the focal of the design focal distance. The next question is, what happens if a metamaterial lens gets dirty? Yeah, a very good question. Sorry, I really can't, not allowed to say much, but commercially, you embed this in an actual polymer. It's got to be a low index polymer. That's what I said. This is a very good question. It has to be done that way, and it works. So that's all what I actually can say. They are indeed encapsulated.
I have
There's a third question.
Oh, I have a question. You made the
Well,
comment.
no, I see the one from Changling Yu. Most publics are made by e-beam, which is accurate but slow. Well, you know, I showed you the examples from Metalenses. Those are done by DQV lithography by a major foundry. So all the high volume application needs to be done by DQV and in the future XUV also. But there are tons of applications that do not require neither multiple wavelengths or achromatic, LiDAR, depth camera, face recognition. Those are done now. You will see products that will appear within the next year by STM in combination with actual Metalenses, done by DQV lithography in amorphous silicon. Yeah, there is another one regarding the design for the inverse max design. Can you use the same design for both max and Dmax? Not really. We thought about it, in fact. So now the effort has been really in making max with multiple. It isn't that simple. In principle, I thought so. A good question, but I really have to think more about it. So this is the fourth question. So I've answered all the questions in the Q&A. I'm sure that there are more. If so, just pick up or write it in the Q&A, please.
You have a question.
I have a question. You made the comment that the efficiency of a metal lens is always less than refractive optics. Why is that? Is it because of anti-reflection coatings?
Well, yeah, well, that's one reason. I mean, you know, we can sort of do impedance matching, but in reality, you have to always contend with diffractive optics, you know, which is essentially, in the simplest way, the underlying physics is that of grating, right? With the unwanted orders of diffraction that try to steal light. Now, those fortunately, by using inversely, these design techniques can be minimized. But I think that's a correct statement. But at the end, you know, I'm not really interested to say that this is so you can only do 96% and refractives might do 99. The fact that there are tons of applications that you don't even need 90%. And but I told you that the company, Metalenses, has done lenses that have exceeded an efficiency of actually 90%. They've talked about it openly at conferences. Of course, the optimization is critical. The inverse, the design, I think it's an advantage. You can do very sophisticated design, not only to have high performance for the lenses, but to do things that simply ordinary optics cannot do. I mean, if you want to make an achromatic lens with a refractive optic, you need to use multiple lenses and multiple materials. So here, I think the multifunctionality is a big winner with actual you know, metaoptics. So in general, this has been so far researched that we and other groups, for example, a group of Andrei Faraon at Caltech, have demonstrated that you can make metasurfaces which have a node, in a sense that you can use the wavelengths or the incident polarization, or to say something about polarization, which I didn't mention, and the angle of incidence, you have to access different functionality by using these three quantities as nodes. Finally, polarization optics. I mean, we have demonstrated the polarization cameras that have simply a single meta lens, a single metasurface, a lens, and a CMOS sensor. Enormously simpler than a conventional. So polarization optics, because you can make metasurfaces where locally you can control the polarization, allows you to do things that you cannot even conceive, cannot even approach with conventional polarization optics that is still primitive, right? It hasn't changed much since the days of the actual biting, seriously. I mean, all these plates are basically birefringent plates. That's it. We use shape birefringents, okay? And the design is such that you can simplify by an enormous amount the complexity of a polarization camera. In fact, we are involved in two programs with NASA Goddard to send these metalenses in the high altitude planes to look at polarization of scattered light from colloids, which is important for studies of climate change.
I have one question. As the design becomes more and more complicated, do you see any room for machine learning for the inverse
absolutely.
design?
Yeah, my group has started to toy with it. Absolutely. That's, it is unavoidable. As a physicist, this is humbling because physicists pride themselves. They have a clever idea. They do it, it works, and they have done great. Now here, you still have to think about the physics, but it's after the fact. You use this technique of inverse design, adjoint optimization, machine learning, and the program spits out a very clever structure. And then sometimes we have to do an enormous effort to understand what is going on here. Why does it behave as such, right? So it is in a sense humbling, but very powerful. So it's unstoppable, I think, the actual trend. Of course, the ideas always count, but it's going to be more and more AI in actual optical design. That's a fact, including inverse, you see, freeform optics, freeform optics, is commercially available for things such as want to make a tiny spectrometer. You basically have to use fancy shape design, freeform optics like toroidal grading. This is complicated stuff. You can do inverse design is a shape of optimization, freeform with actually metaoptics, and do things more compact. And I think this is very very promising. Not immediately, it'll take maybe 4, 5, 6 years.
We have 3 more questions on the Q&A panel. Yes, from Yamin Lu, when will Metalens be commercially used, such as in mobile cameras?
That is one that I cannot, I sort of have an answer. I only can tell you that there'll be camera modules commercially available within a year or so for a variety of applications. But really, I cannot tell you exactly when it's going to be mobile, but it is going to be. They are going to be in mobile, and it's not going to be 5 years. But I am not allowed to give any details of this sort.
And the next question is from Mark. How about reflective optics?
Yeah, reflective optics is an interesting application. I mean, we have used it For the mid-IR, we have made, in fact, efficient metalenses with more than 80% efficiency for the mid-IR mounted on MEMS devices, MEMS tilted mirrors in collaboration with a group at Argonne National Lab. And that's an application for the mid-IR, maybe also for the terahertz, okay. I don't see as many applications as the transmitted ones, but certainly you can optimize also metalens in reflection. You can here use them as deflectors. For example, people are starting to use metasurfaces to deflect light beams. You can even make them tunable, the reflectors and so forth.
Thank you. And there's couple more questions from Michael. Can the optics designs you described to be ported to RF and the microwave regimes?
Yeah, if we can go to the microwave.
Yes.
Yeah, I know people are working in the microwave, but I'm completely non-expert in microwave. So, I mean, the only microwave application we did is for actually modulators. So, but there are groups working on microwave, terahertz. We are starting to explore application because in my group we have developed in the last year a widely tunable terahertz laser, widely tunable for 200 gigahertz to more than a terahertz. And so we are exploring the use of metaoptics to pollinate these terahertz beams. This incidentally is a room temperature laser. There's no cooling needed. It's widely tunable and it is compact. And so we are working on that, but it's in sort of more in the 200, gigahertz per terahertz, not really the smaller microwaves. But there are a number of groups in China also that are working, in the US also, on microwave applications.
Thank you. From Matthew, can you do you perturb an inverse generated design to achieve adjacent optimizations?
Oh, the adjoint optimization is a kind of inverse design. I mean, the RGB lens was designed by adjoint optimization. The multiplexer was designed by adjoint optimization. You can consider that, yes, a type of inverse type of design for sure. I mean, whenever you use, you define an objective function that you try to achieve as close as possible by cycle of optimization. That's one of the goals of inverse design. Now, of course, you can implement it with various platforms, including, deep neural networks, machine learning, as was discussed before.
The final question is from anonymous attendee. Would there be advantages to a periodic or quasi-periodic grids?
Oh, that is a very good question. We published a paper on aperiodic. In fact, some of these lenses are already aperiodic, and some use supercell metasurfaces. We have the paper last year where we showed aperiodic metaoptics, where the unit cell is a supercell, where the metaatoms communicate with each other, and we have shown that this increases tremendously the angular range. Typically, if you unit cell, you can only access a limited set of angles, but if you supercell, we showed we could generate beams at large angle, small angle, without any penalty in efficiency as a function of angle. Also, You can do multifunctional metasurfaces we've used to tune the laser. So definitely, I mean, this paper we published was in Nature Communication last year. And in the title, you see supercell metasurface that talks exactly about, you know, the aperiodic nature.
Okay, thank you very much. I think that's all for the. One more question. Issei Liu from LCU. What is the main difference between Metalens and the hologram?
Well, a hologram in general, you know, people are now using, I mean, for a metal lens, of course, you want to focus light. A hologram, you want to, you have a meta surface, you could have anything else, and you simply design the phase structure. For example, this is the phase only hologram. You can do that with a SLM, with a spatial light modulator that is tunable. And so depending on the phase map that you have designed or implemented dynamically with SLM, you will get, if you look in the far field, you can generate different patterns, different images. Okay, and metasurfaces are a useful approach to holograms, and we are looking this, for example. We have seen that we demonstrated last year that in the far field we can create multiple holograms, different holograms with a single metasurface, and we can go from one hologram to the other by changing the polarization of the incident light. Now, this is very interesting. So you can essentially tune the holograms that you observe by changing the incident polarization. And so this is a nice application of polarization metaoptics applied to holography.
Okay, I think that's all for the question. Thank you very much again.
Okay, thank you.
Thanks for a great talk.
Thank you.